For the longest time, the main question in engineering was pretty straightforward. Can we build it? But as we're all seeing, with challenges like climate change and resources getting scarcer, that question just doesn't cut it anymore. A whole new way of thinking has popped up, one that asks a much, much deeper set of questions. So let's dive into the world of sustainable engineering. Here's the game plan for this explainer. We're going to start with the new ethical code that's really guiding this whole field. Then, we'll unpack something called the triple bottom line. It's the core way to measure success. We'll follow a product's entire journey from cradle to grave, and then see how engineers actually measure what matters. And to wrap it all up, we'll look at some amazing examples of these principles out in the real world. So what exactly is this new ethic all about? Well, it's a huge shift in philosophy. It's about moving past just thinking about technical performance and cost and starting to seriously consider our moral relationship with the planet. This is the kind of tough question that's right at the heart of sustainable engineering. The old way of thinking might have just focused on the industrial growth part of that question, but this new ethic, it forces us to put the environmental and social consequences on the exact same level, really challenging that old idea that nature is just a resource for us to use up. This really brings us to a huge contrast between two different worldviews. For centuries, our thinking has been totally dominated by what's called anthropocentrism. The idea that a forest is only valuable because it gives us wood and oxygen. But the big shift is toward ecocentrism, which is way more holistic. It basically argues that the forest, the river, all its living parts, even the non-living parts, have a right to exist just for their own sake. And this ecocentric view, that's the real philosophical engine driving sustainable engineering. Okay, so how do you take a big philosophy like that and turn it into something practical? I mean, if we're going to engineer things differently, we need a totally new way to score the game, right? And that is exactly where the triple bottom line comes in. The triple bottom line, or TBL for short, was a pretty revolutionary idea when John Elkington introduced it way back in 1994. Think about it. Instead of the one and only bottom line of profit, he proposed a framework that makes us look at three things at once: a company's social impact, its environmental footprint, and its economic performance, all together. These three pillars, often called profit, people, and planet, they aren't fighting each other. They're designed to work in harmony. For the economic pillar, think about solar panels. Yeah, they cost more upfront, but they lead to massive long-term savings. For the social pillar, it's all about people's well-being. A simple footbridge can totally transform a community's access to schools and doctors. And for the environmental pillar, it's about conservation, like a green building that actually collects its own rainwater. A truly sustainable project finds that sweet spot where all three of these things can thrive. Now, to really understand that planet pillar, engineers need a super powerful tool to see the whole picture. It's not enough to just look at a factory smokestack. No. You have to understand the entire life of a product, from the second its raw materials are dug out of the ground until the day it's finally thrown away. And that technique is called a life cycle analysis, or LCA. It's a systematic way to measure the total environmental impact of literally anything, a car, your phone, even a cup of coffee, across its entire existence. It is the ultimate big picture tool for environmental engineering. An LCA breaks a product's life down into 5 main stages. First, you've got to get the raw materials, like mining for metal or harvesting cotton. Then comes all the manufacturing and processing. After that, transportation, which, let's be real, can happen between every single step. Then there's the usage phase. That's us, actually using the thing. And finally, it's end of life. What happens to it? Disposal, recycling, or maybe reuse. And the process for actually doing an LCA is just as structured. It follows international standards. It all starts by defining the goal and scope. Like, what are we measuring here and why? Phase 2 is the inventory analysis, which is basically a huge data gathering mission, tracking every single input and output. Phase 3 is the impact assessment, where all that data gets turned into actual environmental impacts. And finally, interpretation, where you figure out what it all means and how to make better decisions. This definition really just hammers home how incredibly thorough this analysis is. The whole point is to avoid what they call sub-optimization, where you fix a problem in one spot only to accidentally create a much bigger problem somewhere else down the line. LCA makes sure you're looking at the entire system. So when engineers are deep in that impact assessment phase, what are they actually measuring? It's like they say, you can't improve what you don't measure. So having clear, hard numbers is absolutely essential. Here are some of the heavy hitters. The carbon footprint, you've heard of that one. It's all about greenhouse gases. The water footprint tracks all the fresh water used. Now, embodied energy, that one's fascinating. It's all the hidden energy it takes just to produce a material in the first place. Aluminum, for instance, has a crazy high embodied energy. And then you have these combined metrics, like the environmental impact factor, that try to roll a bunch of issues into a single score. And this is where doing an LCA can totally blow your mind. Let's take a simple t-shirt. If I asked you where its carbon footprint comes from, you might guess it's from growing the cotton or maybe shipping it around the world. But a real LCA shows that for this t-shirt, nearly half of its carbon footprint comes from the electricity used during manufacturing. Only 18% is from the cotton itself. This is a perfect example of how this kind of data helps engineers focus their energy where it'll make the biggest difference. Okay, so we've covered the ethics, the frameworks, and the tools. Now for the really fun part. Let's see what this actually looks like when engineers apply these principles to build a more sustainable world. One of the most exciting areas is something called green infrastructure. Instead of just building giant concrete pipes to handle stormwater, engineers are designing systems that actually copy nature. We're talking green roofs, pavements that let water soak through, and urban wetlands. And the cool thing is, these solutions don't just solve one problem. They also clean the air, cool our cities down, and create new habitats for wildlife. And of course, there's the massive field of renewable energy. Sustainable engineering is right at the heart of designing more efficient solar panels, more powerful wind turbines, and building smarter energy grids that can handle all these clean sources and slash our carbon footprint. And really, all of this comes together in sustainable urban planning. It's about completely rethinking the city as a living ecosystem. It means designing cities that are less about cars and more about people, with amazing public transport, tons of green spaces, super energy-efficient buildings, and smart water management. It's about creating cities that are just healthier, fairer, and a lot more resilient. But here's a sobering thought to leave you with. This quote comes from John Elkington, the guy who invented the triple bottom line. Years after he created it, he came back with a warning that these frameworks and tools, they're not enough on their own. Without what he calls radical intent, the serious will to apply these ideas at the speed and scale we need, we risk completely failing to solve our biggest problems. So, at the end of the day, we have the philosophy, we have the frameworks, we have the metrics to build a more sustainable world. We definitely have the engineering smarts. The final, and maybe the hardest, question isn't can we build it anymore? It's will we? How do we, all of us, find that collective will to act with the urgency our planet is demanding?